Picture this for a moment. 300 galaxies, each one blazing with impossible brightness, scattered across the cosmic dawn like ancient beacons that shouldn't exist. Yet there they are, captured by the James Webb Space Telescope, glowing defiantly in the primordial darkness of our universe's infancy. These aren't just any galaxies, they're cosmic rebels, shining so brilliantly in an era when they should barely whisper with light, that they're forcing us to question everything we thought we knew about how the universe began. If you've ever looked up at the night sky and wondered about our cosmic origins, you're about to discover that the story is far stranger and more beautiful than we ever imagined. I'm here to guide you through one of the most profound astronomical discoveries of our time, one that's quietly rewriting the textbook on cosmic evolution while you sleep under those same ancient stars. Take a deep breath and let yourself settle into this moment. As together we journey through space and time, notice how the vastness we're about to explore might shift your perspective on your own place in this mysterious universe. The discoveries we'll uncover aren't just about distant galaxies. They're about the very nature of reality itself. And they're happening right now, in real time, as our most powerful telescope peers deeper into the cosmic past than ever before. To understand why these 300 galaxies are so revolutionary, we need to first understand something beautiful about light itself. Every photon that reaches your eyes right now has been traveling for some amount of time. The light from your lamp traveled almost instantly. Sunlight took 8 minutes to reach you. But starlight, that gentle glow you see on clear nights, has been journeying for years, decades, sometimes millions of years, just to touch your retina. This simple fact transforms every telescope into a time machine. The farther we look into space, the farther back we peer into time. And the James Webb Space Telescope, with its golden mirrors and infrared eyes, can see farther back than any instrument humans have ever built. It can see light that began its journey when the universe was just a fraction of its current age. Imagine the universe as a vast ocean, and we're standing on the shore of the present moment. The James Webb Telescope is like having supernatural vision that lets us see not just the waves lapping at our feet, but ripples that started billions of years ago, when this cosmic ocean was young and wild and fundamentally different from what it is today. The researchers at the University of Missouri understood this when they began their patient work, analysing image after image from Webb's deep field observations. They were digital archaeologists, sifting through cosmic light for clues about an era when the first stars were just beginning to ignite and the first galaxies were taking shape in the primordial darkness. What they found defied their expectations so completely that it's taken months of careful analysis to even begin to understand what they were seeing. These weren't the faint, primitive galaxies that every cosmological model predicted should exist in the early universe. These were cosmic lighthouses, blazing with an intensity that challenges our fundamental understanding of how matter behaves in the infant cosmos. As you listen to this, take a moment to consider the profound patience required for this discovery. Light that left these galaxies over 13 billion years ago, travelling across an expanding universe, finally reached a telescope that took to design decades and build. The researchers then spent months analysing the data, checking and rechecking their findings. You're witnessing the culmination of cosmic timescales and human dedication converging in a single moment of understanding. To appreciate the elegance of how we discover these ancient galaxies, we need to understand one of astronomy's most beautiful techniques. It's called the dropout method, and it's based on a fundamental property of light that connects us directly to the cosmic past. When light travels across vast distances through an expanding universe, something remarkable happens. The light stretches. What started as high-energy ultraviolet light becomes visible light, then infrared, then radio waves. This stretching is called redshift, and it's our cosmic Rosetta Stone, allowing us to decode messages written in starlight billions of years ago. The dropout technique works like cosmic hide-and-seek. Astronomers take pictures of the same patch of sky using different coloured filters. Like looking through different coloured glasses, a galaxy that appears bright when viewed through a red filter, but completely vanishes when viewed through a blue filter, is revealing something profound about its distance and age. This vanishing act happens because of something called the Lyman break, a sharp cut-off in the light spectrum caused by hydrogen gas absorbing ultraviolet photons. It's as if the universe itself is whispering secrets in a code that only careful observation can decipher. When we see this signature in a galaxy's light, we know we're looking at something incredibly ancient, something that existed when the universe was young and hydrogen clouds filled the space between newborn stars. The Missouri team used this technique with Webb's unprecedented sensitivity, scanning 4 patches of sky covering more than 500 square arc minutes. They were essentially casting a net into the cosmic past, and what they caught was extraordinary. 300 objects showing the telltale signs of extreme distance and age, each one brighter than it had any right to be according to our best theories about early galaxy formation. Pause for a moment and imagine the delicate precision required for this work. These researchers were essentially trying to spot candle flames from across a continent, flames that have been burning for longer than complex life has existed on Earth. The fact that we can do this at all speaks to both the power of human ingenuity and the profound orderliness of the physical laws that govern light and matter across cosmic distances. Let's journey back to the era when these mysterious galaxies first began to shine. We're travelling not just through space, but through time itself, back to when the universe was less than 1 billion years old. To put this in perspective, if the universe's entire history were compressed into a single year, we're looking at events that happened in early February, when the cosmic calendar had barely begun. This was an era unlike anything we see in the universe today. The cosmic microwave background, that faint afterglow of the Big Bang, was still relatively warm. Dark matter, that mysterious substance that makes up most of the universe's mass, was just beginning to clump together into the scaffolding upon which galaxies would eventually form. The first stars had recently ignited, transforming hydrogen and helium into heavier elements through nuclear fusion in their cores. According to our best understanding of cosmic evolution, this should have been a time of modest beginnings. Early galaxies should have been small, dim, and struggling to grow. They should have been converting gas into stars inefficiently, taking their time to build up mass and brightness. The universe was denser then, yes, but it was also more chaotic, with frequent collisions and disruptions that should have made it difficult for large, stable structures to form quickly. Yet here are these 300 galaxies blazing with luminosity that suggests they're converting nearly 100% of their available gas into stars. In the modern universe, we typically see galaxies converting at most 10% of their gas into stars, with the rest being blown away by stellar winds and supernova explosions. These ancient galaxies appear to be operating under completely different rules. As you contemplate this, notice how it mirrors something profound about growth and potential in your own life. Sometimes the most unexpected breakthroughs happen not when conditions are perfect, but when they seem most challenging. These galaxies are teaching us that the universe itself might be far more dynamic and surprising than our models suggest. The James Webb Space Telescope itself deserves our contemplation as we dive deeper into this discovery. This isn't just a larger version of the Hubble Space Telescope. It's a fundamentally different kind of instrument, designed specifically to capture the infrared light that carries messages from the cosmic dawn. Webb's primary mirror, composed of 18 hexagonal segments coated in gold, spans 6.5 meters across when fully deployed. But size alone doesn't explain its revolutionary capabilities. The telescope operates at incredibly cold temperatures, about -223 degrees Celsius, achieved by positioning it at a special point in space called L2, where it hides in Earth's shadow while orbiting the Sun. This extreme cold is essential because infrared light is heat radiation. If the telescope itself were warm, it would be like trying to observe faint stars while standing next to a bonfire. By cooling Webb to just above absolute zero, engineers created an instrument sensitive enough to detect the heat signature of a bumblebee on the Moon. The Missouri team relied specifically on two of Webb's most sophisticated instruments: the Near-Infrared Camera, or NIRCAM, which captures detailed images across a range of infrared wavelengths, and the Mid-Infrared Instrument, or MIRI, which can detect even longer wavelengths that reveal different aspects of cosmic objects. These instruments work together like a cosmic symphony, each contributing its own voice to the chorus of discovery. NIRCam might detect the overall shape and brightness of a distant galaxy, while MIRI reveals details about its composition and the processes happening within it. Together, they create a portrait of cosmic objects that no previous telescope could achieve. Take a moment to appreciate the remarkable journey that brought these instruments into existence. Thousands of engineers, scientists, and technicians worked for decades to design, build, test, and deploy this observatory. The gold coating on its mirrors was applied atom by atom. The cooling systems were tested in vacuum chambers that simulate the conditions of deep space. Every component had to work flawlessly, because unlike Hubble, Webb is too far from Earth for repair missions. As the Missouri team began analysing their 300 candidates more carefully, the mystery only deepened. Using a technique called spectral energy distribution analysis, they attempted to determine the distance, age, and mass of each object. This process is like being a cosmic detective, gathering clues from the fingerprint of light that each galaxy leaves across the electromagnetic spectrum. What they found challenged expectations in multiple ways. More than 80% of their candidates turned out to be what astronomers call extremely red objects, meaning their light was dramatically brighter in longer infrared wavelengths compared to shorter ones. This extreme redness could indicate several possibilities, each with profound implications for our understanding of cosmic evolution. Some of these objects might indeed be the ancient galaxies they appear to be, shining with impossible brightness in the cosmic dawn. Others might be closer galaxies whose light is heavily obscured by dust, creating a reddening effect similar to how Earth's atmosphere makes the setting sun appear orange or red. Still others might be something entirely unexpected, perhaps massive black holes in the early universe, growing and glowing as they consume primordial gas and matter. The challenge facing the research team illustrates something beautiful about the scientific process. Each answer leads to new questions. Each measurement opens up new possibilities. Rather than simply confirming what we already knew, these observations are forcing us to expand our understanding of what's possible in the universe. One galaxy in their sample, designated JADESG has already been confirmed through detailed spectroscopy to be genuinely ancient, existing when the universe was only about 300 million years old. This single confirmation proves that at least some of these bright early objects are real and not observational errors or misidentified closer galaxies. But one confirmation only makes the broader question more intriguing. If JD's GSZ14-0 is real and representative, then we're looking at a population of early galaxies that grew massive and bright far more quickly than any of our models predict. These aren't just minor adjustments to cosmic evolution, they're fundamental challenges to our understanding of how matter behaves in the early universe. As you reflect on this unfolding mystery, consider how it mirrors the way understanding grows in any field. Often, our most profound insights come not from confirming what we already believe, but from encountering phenomena that force us to question our basic assumptions and expand our vision of what's possible. The implications of these discoveries ripple outward like waves in a cosmic pond, touching nearly every aspect of our understanding of how the universe evolved from its smooth, nearly uniform beginning to the rich tapestry of galaxies, stars, and planets we see today. If even a fraction of these 300 candidates prove to be genuine early galaxies, we'll need to fundamentally reconsider the efficiency of star formation in the primordial universe. Current models suggest that early galaxies should have been relatively inefficient at converting gas into stars, with most of the available material being blown away by stellar winds and supernova before it could contribute to galactic growth. These observations suggest the opposite might be true. Perhaps conditions in the early universe, with its higher density and different chemical composition, actually favoured rapid, efficient star formation. Perhaps the lack of heavy elements, which we now know can cool gas and regulate star formation, actually made the process more violent and productive in those ancient times. The discovery also raises profound questions about the role of dark matter in early cosmic evolution. Our current understanding suggests that galaxies form within halos of dark matter, invisible scaffolding that provides the gravitational framework for ordinary matter to collect and form stars. But the number of massive galaxies Webb is finding in the early universe might exceed the number of dark matter halos that should have existed at that time. This tension between observation and theory is pushing some astronomers to consider alternative explanations for cosmic evolution. Some are exploring modified theories of gravity that might allow structures to form more quickly in the early universe. Others are investigating whether our understanding of dark matter itself needs revision. Even more intriguingly, some of these early galaxies appear to harbour supermassive black holes at their centres, objects containing millions or billions of times the mass of our Sun. The presence of such massive black holes so early in cosmic history presents its own puzzle. How could these giants have formed and grown so quickly when the universe itself was still in its infancy? These questions don't have easy answers, and that's precisely what makes this discovery so compelling. Science advances not just through confirmation of existing theories, but through encounters with phenomena that push the boundaries of our understanding and force us to think in new ways about the fundamental nature of reality. Take a breath and consider how this process of discovery mirrors growth and understanding in your own life. Often our most profound personal insights come not when everything fits neatly into our existing worldview, but when we encounter experiences that challenge us to expand our vision and embrace new possibilities. The journey into cosmic mysteries continues, and we're only beginning to understand what these 300 rebellious galaxies are teaching us about the universe's hidden nature. As we prepare to delve even deeper into the implications of this discovery, remember that you're witnessing science in action. The eternal human quest to understand our place in a cosmos that continues to surprise and inspire us with its profound mysteries. In our next exploration, we'll examine the revolutionary techniques that made this discovery possible and consider what these findings might mean for our understanding of cosmic evolution and our own place in this vast, ever-surprising universe. As we drift deeper into this cosmic mystery, there's something almost meditative about contemplating how light itself becomes our messenger from the deep past. Each photon captured by Webb's golden mirrors has been travelling through the expanding fabric of space-time for over 13 billion years, carrying within its wavelength the story of galaxies that may no longer even exist. The researchers discovered that analysing these ancient light signatures requires a kind of scientific poetry. They must read the subtle variations in brightness across different infrared wavelengths, like astronomers reading cosmic sheet music, where each note tells part of a larger symphony about stellar birth, galactic evolution, and the fundamental forces that shaped our universe's earliest chapters. What makes this discovery particularly fascinating is how it reveals the universe's capacity for surprise. These 300 galaxies aren't just brighter than expected, they're brighter in ways that suggest completely different physical processes were at work in the cosmic dawn. Some appear to be converting gas into stars with an efficiency that approaches theoretical limits, while others show signatures that hint at supermassive black holes already feeding at their centres when the universe was barely 3% of its current age. Take a moment to consider what this means for our understanding of time itself. We're not just looking at old galaxies, we're glimpsing an era when the laws of physics may have manifested in ways we've never directly observed. The density of matter was higher, the temperature of space was warmer, and the very chemistry of the cosmos was fundamentally different from what we see around us today. As you listen to this, notice how the concept of deep time might shift your perspective on the temporary nature of our own concerns and the enduring patterns that connect us to this ancient cosmic story. To truly understand what these galaxies are telling us, we need to appreciate the elegant detective work involved in spectroscopic analysis. When astronomers spread the light from these distant objects across its component wavelengths, they're essentially performing cosmic archaeology, reading the chemical signatures written in starlight over 13 billion years ago. Each element in the universe leaves its own unique fingerprint in the light spectrum. Hydrogen, the universe's most abundant element, creates specific absorption and emission lines. Helium, forged in the Big Bang itself, has its own signature. Heavier elements like carbon, oxygen, and iron, which can only be created in the nuclear furnaces of massive stars, tell us about the generations of stellar evolution that preceded what we're observing. What's remarkable about these early galaxies is that some of them already show evidence of heavy element enrichment, suggesting that massive stars lived, died, and scattered their nuclear ashes into space far more quickly than our models predict. It's as if the universe was writing its chemical story in fast forward during those early epochs. The spectroscopic confirmation process represents one of humanity's most sophisticated attempts to decode messages from the cosmic past. Each spectrum requires hours or even days of telescope time to collect enough photons for analysis. The light from these galaxies is so faint that capturing a single spectrum is like trying to analyze the chemical composition of a candle flame viewed from the distance of the moon. Yet, as it has for objects when that analysis succeeds, like Jardé's GS 14-0, we gain direct access to the physical conditions that existed when just the distance their mass, their rate of star formation, can measure, not our universe, was in its infancy. We can measure not only the distance, mass and age of these galaxies, but even the properties of the supermassive black holes that may lurk at their centres. Pause for a moment and consider the profound patience required for this kind of discovery. The light we're analysing began its journey toward us when complex life on Earth consisted of nothing more than simple single-celled organisms. That same light, carrying its coded message about cosmic dawn, finally reaches our instruments, just as humanity has developed the technology to decode its meaning. The implications of these discoveries extend far beyond astronomy into the realm of fundamental physics and cosmology. Our current understanding of how the universe evolved, known as the lambda-cold dark matter model, has successfully explained countless observations over the past several decades. Yet these bright early galaxies are pushing against the very foundations of this well-established framework. The standard model predicts that structure formation in the early universe should have been a gradual process. Dark matter, making up roughly 85% of all matter, should have slowly clumped together under gravity, creating the scaffolding upon which ordinary matter could collect to form the first stars and galaxies. This process should have taken time, resulting in small dim galaxies that only gradually grew larger and brighter over cosmic epochs. Instead, Webb is revealing a universe where massive luminous galaxies appeared remarkably early in cosmic history. Some of these objects contain stellar masses approaching billions of times that of our Sun, achieved when the universe was less than 5% of its current age. To put this in perspective, it's like finding fully grown oak trees in a forest that should contain only seedlings. The challenge isn't just observational, it's theoretical. For galaxies to grow this massive this quickly, they would need to convert nearly all of their available gas into stars, a process that should be impossible given our understanding of stellar feedback mechanisms. When massive stars form, they generate powerful winds and eventually explode as supernova, processes that typically blow away much of the remaining gas and halt further star formation. These early galaxies seem to have operated under different rules, perhaps because the higher density of the early universe made it harder for stellar winds to escape, or because some unknown physical process enhanced the efficiency of star formation in ways we don't yet understand. Some researchers are beginning to explore whether our understanding of dark matter itself needs revision. Alternative theories of gravity, such as modified Newtonian dynamics, predicted decades ago that structure formation might proceed more rapidly than the standard model suggests. While these theories remain controversial, the Webb observations are giving them renewed attention. As you contemplate these challenges to establish scientific understanding, notice how they mirror the way personal growth often requires us to question our fundamental assumptions about how the world works. Sometimes our most profound insights come not from confirming what we already believe, but from embracing observations that force us to expand our vision of what's possible. Among the most intriguing aspects of these early galaxy discoveries is the growing evidence that many of them harbour supermassive black holes at their centres, objects containing millions or even billions of times the mass of our Sun. The presence of such massive gravitational monsters so early in cosmic history presents a puzzle that's keeping cosmologists awake at night. Black holes grow by consuming matter, and the rate at which they can grow is limited by fundamental physics. As material falls into a black hole, it heats up and glows brilliantly, creating what astronomers call an accretion disk. This glowing material generates radiation pressure that pushes away additional infalling matter, creating a natural speed limit for black hole growth known as the Eddington limit. Even if a black hole formed immediately after the Big Bang and grew continuously at this maximum rate, it should be impossible for it to reach supermassive proportions in the time available in the early universe. Yet Webb is finding evidence of billion solar mass black holes existing when the universe was less than 1 billion years old. This presents us with what cosmologists call the black hole seed problem. How did these massive objects get started? One possibility is that the first stars were much more massive than anything we see today, collapsing directly into intermediate mass black holes that could serve as seeds for rapid growth. Another possibility is that primordial black holes formed directly from density fluctuations in the early universe, bypassing stellar evolution entirely. Some researchers are exploring even more exotic possibilities. Perhaps black holes in the early universe could grow faster than the Eddington limit under certain conditions. Perhaps they formed through entirely unknown processes that only operated in the extreme conditions of the cosmic dawn. The relationship between these early supermassive black holes and their host galaxies adds another layer of mystery. In the modern universe, there's a tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge, suggesting that galaxies and their central black holes grow together through cosmic time. But in these early systems, the black holes appear to be much more massive relative to their host galaxies than we see today. This suggests that the co-evolution of galaxies and black holes might have followed different patterns in the early universe. Perhaps black holes formed first and helped trigger rapid star formation in their host galaxies. Or perhaps both grew through some unknown process that operated more efficiently in the dense, hot conditions of cosmic dawn. Take a breath and consider how these cosmic mysteries reflect something profound about growth and development in any complex system. Sometimes the most important elements emerge first, creating the framework within which everything else can develop. These early black holes might have been the cosmic architects, shaping the formation of galaxies in ways we're only beginning to understand. To fully appreciate the elegance of this discovery, we need to dive deeper into the dropout technique that made it possible. This method represents one of astronomy's most beautiful examples of turning a limitation into a tool for discovery. The technique relies on a fundamental property of hydrogen, the universe's most abundant element. Hydrogen atoms absorb ultraviolet light at very specific wavelengths, creating what's called the Lyman series of absorption lines. The strongest of these, known as the Lyman alpha line, occurs at a wavelength of 121.6 nanometers in the ultraviolet part of the spectrum. In distant galaxies, this absorption creates a sharp cutoff in the observed spectrum called the Lyman break. Light at wavelengths shorter than this break gets absorbed by intervening hydrogen clouds, while longer wavelengths pass through relatively unimpeded. It's as if the universe itself is applying a filter to the light from distant galaxies. As light travels across cosmic distances through expanding space, this break gets redshifted to longer and longer wavelengths. For galaxies at moderate distances, the break appears in the visible part of the spectrum. For the most distant galaxies, it shifts into the infrared, precisely where Webb's instruments are most sensitive. The dropout technique works by taking images of the same region of sky through multiple filters, each sensitive to different wavelengths of light. A galaxy that appears bright in longer wavelength images, but completely disappears in shorter wavelength images, is revealing the position of its Lyman break, which directly indicates its distance and age. What makes this technique so powerful is its efficiency. Rather than requiring lengthy spectroscopic observations of individual objects, astronomers can survey large areas of sky and identify thousands of candidate distant galaxies in a single set of observations. It's like casting a wide net into the cosmic past and catching everything that meets specific criteria. The Missouri team applied this technique with unprecedented precision, using Webb's extraordinary sensitivity to probe deeper into the infrared than any previous survey. They were essentially fishing in cosmic waters that no one had ever explored, and what they caught exceeded all expectations. But the dropout technique also has limitations. It can identify candidate distant galaxies, but it cannot definitively prove their nature without follow-up spectroscopy. Some objects that appear to be distant galaxies might actually be closer objects, whose light is reddened by dust. Others might be more exotic phenomena that mimic the signatures of distant galaxies. This is why spectroscopic follow-up observations are so crucial. Only by spreading the light from these objects across their full spectrum can astronomers definitively measure their distances, compositions, and physical properties. Each confirmed distant galaxy represents hours or days of precious telescope time, but the scientific payoff is enormous. As you consider this interplay between efficient survey techniques and detailed follow-up observations, notice how it mirrors the balance between broad exploration and focused investigation that characterizes learning in any field. Sometimes we need to cast a wide net to discover new possibilities, and sometimes we need to examine specific cases with extraordinary care to understand what we found. As we look toward the future of this research, we're standing at the threshold of a new era in cosmic archaeology. The James Webb Space Telescope represents just the beginning of our ability to probe the deepest layers of cosmic history, and the discoveries we've explored today are likely just the first glimpse of revelations to come. The next phase of research will focus on spectroscopic confirmation of these galaxy candidates. Each spectrum will provide a definitive measurement of distance and reveal details about stellar populations, chemical composition, and physical conditions that existed in these ancient systems. This painstaking work will determine how many of the 300 candidates are genuine early galaxies, and how many might be other types of objects masquerading as distant cosmic beacons. Future observations will also probe the relationship between these early galaxies and the cosmic web of dark matter that presumably supports them. By studying how these bright early galaxies are distributed across the sky, astronomers can test whether their clustering properties match predictions of structure formation models. The discovery also opens new avenues for understanding rionization, the epoch when the first stars and galaxies flooded the universe with ultraviolet light, transforming neutral hydrogen into ionized plasma. If early galaxies were more numerous and luminous than previously thought, they might have contributed more significantly to this cosmic phase transition than current models suggest. Technological advances beyond Webb will push these investigations even further. The next generation of ground-based telescopes with mirrors 30 meters in diameter, will have the light-gathering power to conduct detailed spectroscopy of objects too faint for current instruments. Space-based successors to Webb are already in development, designed to probe even deeper into the cosmic past with unprecedented precision. Perhaps most intriguingly, these discoveries are prompting theoretical physicists to reconsider fundamental assumptions about cosmic evolution. New models of star formation, black hole growth, and structure formation are being developed to account for the rapid pace of early galactic development that Webb is revealing. The intersection of observation and theory in cosmology reminds us that science is not just about collecting data, but about weaving that data into coherent narratives that help us understand our place in the cosmic story. Each new observation has the potential to revise that narrative in profound ways. As you reflect on this ongoing process of discovery, consider how it parallels the way understanding develops in your own life. We build models of how we think the world works, but remain open to observations that might require us to revise those models. The most profound growth often comes from embracing evidence that challenges our existing assumptions. The 300 mysterious galaxies discovered by Webb are teaching us that the universe's story is far more complex and surprising than we imagined. They remind us that cosmic evolution, like personal growth, rarely follows the smooth, predictable path as we might expect. Instead, it's filled with sudden bursts of creativity, periods of rapid transformation, and moments when the impossible becomes inevitable. In our continuing exploration of cosmic mysteries, we're learning not just about distant galaxies, but about the fundamental nature of time, space, and the forces that shape reality itself. As we prepare to delve even deeper into these cosmic revelations, remember that you're witnessing one of humanity's greatest adventures, the quest to understand our origins in a universe that continues to surprise and inspire us with its profound mysteries. This journey through cosmic time connects us directly to our next exploration, where we'll discover how the quantum nature of reality itself might be shaping the decisions you make every moment of your day. The same universe that birthed these ancient galaxies operates according to quantum principles that some interpretations suggest might influence the very fabric of choice and possibility in your daily life. Join me as we explore the quantum decision that's already shaping your future, where the mysteries of cosmic evolution meet the intimate reality of human experience. As we drift deeper into contemplating these 300 cosmic rebels, there's something profoundly humbling about how they're reshaping our understanding of cosmic architecture itself. The universe, it seems, was far more dynamic and creative in its youth than we ever dared imagine. The traditional picture of early cosmic evolution resembled a slow, methodical construction project. Dark matter would gradually clump together under gravity's patient pull, forming invisible scaffolding. Ordinary matter would then collect within these dark matter halos, slowly cooling and condensing into the first stars. These early stars would live brief, violent lives before exploding and enriching space with heavier elements. Only then, according to our models, could the second generation of stars form more efficiently, eventually building the massive luminous galaxies we see in the nearby universe. But Webb's observations are revealing a universe that apparently skipped several chapters of this cosmic textbook. These ancient galaxies appear to have achieved remarkable size and brightness with startling efficiency, as if the early universe possessed some hidden accelerator that we're only now beginning to glimpse. Consider for a moment how this mirrors patterns of growth and transformation in your own experience. Sometimes the most significant changes happen not through gradual, accumulation, but through sudden leaps that seem to defy the expected timeline. These galaxies are teaching us that the universe itself might operate according to principles of rapid transformative growth that we're only beginning to understand. The spectroscopic analysis of these objects reveals another layer of cosmic mystery. When astronomers decompose their light into component wavelengths, they're finding chemical signatures that tell stories of accelerated stellar evolution. Some of these galaxies show evidence of heavy elements like carbon, nitrogen, and oxygen in abundances that suggest multiple generations of massive stars had already lived and died in the cosmic dawn. This chemical enrichment should have taken hundreds of millions of years to achieve, yet we're seeing it in galaxies that existed when the universe was barely past its third birthday. It's as if these ancient stellar nurseries operated according to different temporal rules, compressing what should have been eons of gradual evolution into cosmically brief episodes of intense creativity. What makes these discoveries particularly fascinating is how they illuminate the delicate dance between order and chaos that has shaped cosmic evolution from its earliest moments. The universe began in a state of near-perfect smoothness, with matter distributed almost uniformly throughout space. Yet somehow, from this smooth beginning, emerged the rich structure we see today. Galaxies, stars, planets, and ultimately, conscious observers capable of contemplating their own cosmic origins. The process that transforms cosmic smoothness into galactic complexity involves a delicate interplay between gravitational attraction, which tries to pull matter together, and cosmic expansion, which tries to spread it apart. Add to this the complex physics of gas dynamics, stellar feedback, and magnetic fields, and you have a system of extraordinary subtlety and sophistication. These bright early galaxies suggest that this dance between order and chaos might have followed different rhythms in the cosmic dawn. Perhaps the higher density of the early universe tipped the balance more strongly toward gravitational collapse, allowing structures to form more rapidly than they do today. Perhaps the absence of heavy elements, which in the modern universe help regulate star formation by cooling interstellar gas, actually made the process more violent and efficient in those ancient times. Some theoretical models are exploring whether the early universe might have experienced brief periods of accelerated structure formation, cosmic growth spurts that could explain the rapid appearance of massive galaxies. These models suggest that the interplay between dark matter, ordinary matter, and the expanding space-time fabric might have created temporary windows of enhanced gravitational efficiency. Take a breath and consider how this cosmic story of rapid transformation resonates with moments in your own life when circumstances aligned to create periods of unexpected growth and change. The universe, it seems, is teaching us that evolution, whether cosmic or personal, rarely follows the smooth, predictable curves we might expect. One of the most intriguing aspects of this discovery is what it suggests about the uniqueness of our cosmic neighbourhood. For decades, astronomers have wondered whether the Milky Way and its local group of galaxies represent typical examples of cosmic structure, or whether we might inhabit a particularly special region of space. The abundance of bright, massive galaxies that Webb is discovering in the early universe suggests that rapid galaxy formation might have been more common than we previously thought. This has profound implications for our understanding of cosmic demographics and the likelihood of finding other regions of space capable of supporting complex chemistry and ultimately life. If massive galaxies formed more readily in the early universe, they would have begun enriching space with heavy elements sooner than our models predicted. carbon, oxygen, silicon, iron, all the elements essential for rocky planets and organic chemistry would have become available for incorporation into new stellar systems earlier in cosmic history. This chemical enrichment process is crucial for understanding the cosmic timeline of habitability. Stars like our Sun, which formed relatively late in cosmic history, inherited a rich mixture of heavy elements from previous generations of stellar evolution. But if heavy element production began earlier and proceeded more rapidly than we thought, it might mean that potentially habitable planetary systems could have formed billions of years before our solar system came into existence. The implications stretch beyond mere academic curiosity. If complex chemistry became possible early in cosmic history, and if massive galaxies provided the stellar furnaces necessary for heavy element production, then the universe might have been capable of supporting complex structures, and perhaps even life, far earlier than we previously imagined. As you contemplate these possibilities, notice how they invite us to reconsider our place in the cosmic timeline. We often think of ourselves as products of a young universe, still in its early stages of development. But these discoveries suggest we might actually be relative latecomers to a cosmos that has been experimenting with complexity for most of its existence. The instruments that made this discovery possible represent humanity's most sophisticated attempt to build actual time machines. While science fiction imagines time travel through exotic technologies involving wormholes or paradoxes, astronomers achieve it through the patient accumulation of ancient photons that have been traveling toward us across cosmic distances for billions of years. Webb's revolutionary capabilities stem not just from its size, but from its exquisite thermal control and wavelength sensitivity. Operating at temperatures just above absolute zero, the telescope can detect infrared radiation so faint that it's equivalent to sensing the heat from a candle on the moon. This extraordinary sensitivity allows it to capture photons that began their journey when the universe was a fraction of its current age. The process of cosmic archaeology requires remarkable precision. Each photon carries information encoded in its wavelength, intensity, and polarization. By carefully analyzing these properties across thousands of cosmic sources, astronomers can reconstruct the physical conditions that existed in distant galaxies billions of years ago. Consider the profound patience required for this kind of investigation. The light we're analyzing left these galaxies before Earth had formed, before our Sun had ignited, before the heavy elements that make up our bodies had been forged in stellar cores. That same light, carrying its coded message about cosmic dawn, arrives at our detectors just as human civilization has developed the technology to decode its meaning. The data processing involved in this discovery represents another form of technological marvel. Each image from Webb contains millions of pixels, each pixel containing information about the light from a tiny patch of sky. Sophisticated algorithms sift through this data, identifying patterns and anomalies that might indicate the presence of distant galaxies. The researchers who made this discovery spent months carefully calibrating their analysis techniques, checking for systematic errors, and validating their results against known standards. It's a process that combines cutting-edge technology with old-fashioned scientific rigor, where every claim must be supported by multiple lines of evidence. Pause for a moment and appreciate the remarkable convergence of human ingenuity and cosmic timing that made this discovery possible. The universe had to exist for billions of years. Stars had to form and create heavy elements. Planets had to coalesce. Life had to evolve and develop intelligence. And human civilization had to advance to the point where we could build instruments sensitive enough to detect these ancient cosmic, the philosophical beacons. These discoveries invite us to contemplate profound questions about the nature of time, causality, and our place in the cosmic story. When we observe these ancient galaxies, we're not just looking at distant objects. We're witnessing events that happened billions of years ago, events that helped shape the very conditions that eventually allowed our own existence. There's something almost mystical about the realization that the light entering our eyes right now left these galaxies when the universe was young and wild and fundamentally different from what it is today. We're not separate observers looking at an external cosmos. We're participants in an ongoing cosmic story, connected to these ancient events through the photons that have been travelling toward us across space and time. The philosophical implications extend beyond mere wonder at cosmic vastness. These discoveries challenge us to think about the relationship between observation and reality itself. The galaxies we're observing existed billions of years ago, but our observation of them is happening now in the present moment. In some sense, the act of observation is bringing these ancient events into our contemporary experience. This interplay between past and present, between observation and reality, echoes some of the deepest questions in philosophy and physics. What does it mean to say that these galaxies existed in the past when our only evidence for their existence is the light reaching us now? How do we reconcile the objective reality of cosmic evolution with the subjective experience of discovery and understanding? Some interpretations suggest, though this remains deeply speculative, that consciousness itself might play a role in how we construct our understanding of cosmic history. Not that our thoughts create reality, but that the act of conscious observation is what transforms raw data into meaningful knowledge about the universe's past. Take a moment to reflect on how this cosmic perspective might influence your understanding of time and change in your own life. We often experience time as a linear progression from past to future, but these astronomical discoveries remind us that past, present, and future are intimately connected in ways that transcend our everyday experience. As we look toward the future of cosmology, these discoveries are opening new frontiers of investigation that will likely reshape our understanding of cosmic evolution for decades to come. The questions raised by these 300 mysterious galaxies will require new theoretical frameworks, more sophisticated observational techniques, and perhaps fundamentally new ways of thinking about how the universe works. The next generation of space telescopes is already in development, instruments with even greater sensitivity and resolution than Webb. These future observatories will be able to study individual stars within distant galaxies, probe the properties of their supermassive black holes, and trace the detailed chemical evolution of cosmic structures across billions of years of history. Ground-based telescopes are also evolving rapidly, with mirror diameters approaching 30 meters and adaptive optic systems that can correct for atmospheric disturbances in real time. These instruments will complement space-based observations, providing the light-gathering power necessary for detailed spectroscopic studies of the faintest cosmic objects. But perhaps the most exciting developments will come from the intersection of observation and theory. The challenges posed by these bright early galaxies are stimulating new mathematical models of cosmic evolution, simulations that attempt to reproduce the observed properties of early galaxies within our current understanding of fundamental physics. Some of these models are exploring exotic possibilities, rapid black hole growth, super-efficient star formation, or even modifications to our understanding of dark matter and gravity. While most of these ideas remain highly speculative, they represent the kind of creative thinking that often precedes major scientific breakthroughs. The discovery is also inspiring new approaches to data analysis and machine learning. With millions of cosmic objects in each Webb image, astronomers are developing artificial intelligence algorithms that can identify patterns and anomalies that human observers might miss. These techniques are revealing subtle correlations in cosmic data that might provide clues to physical processes we don't yet understand. As you contemplate this ongoing process of discovery and understanding, consider how it mirrors the way knowledge grows in any field. New observations challenge existing theories, forcing scientists to develop more sophisticated models. These models make new predictions, which inspire new observations, creating a cycle of discovery that drives scientific progress. Perhaps one of the most beautiful aspects of this discovery is how it illuminates the deep interconnectedness of cosmic evolution. These ancient galaxies didn't form in isolation. They were part of a vast cosmic web of dark matter and ordinary matter that has been evolving and growing more complex throughout the universe's history. The large-scale structure of the universe resembles a three-dimensional spider web, with galaxies forming along filaments of dark matter that stretch across hundreds of millions of light-years. The early galaxies discovered by Webb represent some of the first bright nodes in this cosmic web, the points where matter began to collect and condense into the structures we see today. Understanding how these early bright spots relate to the overall architecture of cosmic structure is one of the key challenges facing astronomers. Were these galaxies forming at special locations in the cosmic web where matter was particularly dense, or do they represent a phase of cosmic evolution when galaxy formation was more efficient everywhere? The answers to these questions will help us understand not just the history of individual galaxies, but the evolution of cosmic structure as a whole. They might also provide clues about the nature of dark matter itself, the mysterious substance that provides the gravitational scaffolding for all cosmic structure. Some theoretical models suggest that the properties of dark matter particles might have been different in the early universe, allowing structures to form more rapidly than they do today. Other models propose that the interaction between dark matter and ordinary matter might have been stronger in the dense conditions of cosmic dawn. These investigations are pushing the boundaries of both observational astronomy and theoretical physics. They require us to think about phenomena that operate on scales ranging from subatomic particles to cosmic superclusters, over time periods spanning from microseconds to billions of years. Take a breath and consider how this cosmic web of connection might resonate with your own experience of interconnectedness. Just as these ancient galaxies are connected to us through the light that has travelled across space and time, we're connected to each other and to the natural world through networks of relationship and influence that often operate below the threshold of conscious awareness. As we near the end of our journey through this cosmic mystery, it's worth reflecting on what these 300 rebellious galaxies are ultimately teaching us about the nature of existence itself. They're not just astronomical objects, they're messengers from the cosmic dawn, carrying information about conditions and processes that existed when the universe was young and everything seemed possible. Their message is one of surprise and possibility. The universe, they tell us, is far more creative and dynamic than our models suggested. The cosmic story is not one of slow, predictable evolution, but of sudden leaps, rapid transformations, and unexpected emergences of complexity and beauty. These ancient galaxies remind us that the universe has been experimenting with structure and organization for most of its existence. They suggest that creativity and rapid change are not recent developments, but fundamental features of cosmic evolution that have been operating since the earliest moments of the universe's history. There's something deeply inspiring about this cosmic perspective. It suggests that the capacity for growth, transformation, and the emergence of new possibilities is built into the very fabric of reality. From the formation of the first galaxies to the evolution of consciousness, the universe seems to possess an inherent tendency toward increasing complexity and beauty. The discovery also reminds us of our profound connection to cosmic history. The elements in our bodies were forged in the cores of massive stars, possibly including some of the bright early galaxies we've been discussing. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of these elements were created billions of years ago in stellar furnaces that we can now observe through Webb's golden mirrors. This connection goes beyond mere chemistry. The physical laws that govern the formation and evolution of galaxies are the same laws that govern the biochemical processes in our bodies, the neural activity in our brains, and the social dynamics of human civilization. We're not separate from the cosmic story, we're expressions of it. As you reflect on this cosmic connection, notice how it might influence your sense of purpose and belonging. We often feel isolated in our daily concerns, but these discoveries remind us that we're participants in a story that began with the Big Bang and continues to unfold through our thoughts, actions, and relationships. The 300 mysterious galaxies discovered by Webb are teaching us that the universe is far stranger, more beautiful, and more creative than we ever imagined. They invite us to embrace uncertainty, to remain open to surprise, and to find wonder in the ongoing process of discovery that connects us to the deepest mysteries of existence. As we conclude this exploration of cosmic mysteries, remember that the same universe that birthed these ancient galaxies continues to operate through the quantum processes that govern reality at its most fundamental level. In our next journey together, we'll discover how the quantum nature of reality itself might be influencing the very decisions you make every moment of your day, connecting cosmic evolution to the intimate reality of choice and possibility in the quantum decision that's already shaping your future. As we drift further into contemplating these cosmic mysteries, there's something almost paradoxical about the timing of this discovery. Here we are, in what we might consider the middle age of the universe, finally developing the technology to glimpse its infancy. The universe had to exist for 13.8 billion years. Stars had to live and die, heavy elements had to be forged and scattered, planets had to form, life had to evolve, and consciousness had to emerge, all so that we could look back and witness the very events that set this entire chain in motion. It's as if the universe has been telling itself a story for billions of years, and we've only just learned to read the ancient chapters written in starlight. These 300 galaxies represent pages from the universe's earliest draft, passages that reveal a cosmic narrative far more complex and surprising than the simplified version we thought we understood. The researchers analysing Webb's data describe their work as a form of cosmic archaeology, but it's more profound than that metaphor suggests. Archaeologists dig through layers of Earth to uncover artifacts from human civilizations. These astronomers are digging through layers of time itself, uncovering the remnants of cosmic civilizations, stellar communities that flourished when the universe itself was barely recognizable. Each spectrum they analyze is like discovering an ancient manuscript written in a language of hydrogen lines and stellar winds. Each confirmed redshift measurement is like carbon dating a cosmic artifact, placing it precisely in the timeline of universal evolution. The process requires not just technological sophistication, but a kind of temporal imagination, the ability to envision conditions and processes that no longer exist anywhere in the observable universe. Take a moment to consider how this process of cosmic discovery mirrors the way memory works in your own consciousness. We reconstruct past experiences from fragments of sensory information, emotional impressions, and contextual clues. Similarly, astronomers reconstruct the cosmic past from fragments of light that have been traveling toward us across unimaginable distances and timescales. The difference is that cosmic memory is more reliable than human memory. The light from these ancient galaxies carries an unedited record of physical conditions that existed billions of years ago. Unlike human recollections, which can be altered by emotion and expectation, the spectral lines in starlight preserve an objective chronicle of temperature, density, chemical composition, and motion with extraordinary fidelity. What's emerging from these observations is a picture of early galactic ecosystems that operated according to principles we're only beginning to understand. These weren't isolated islands of stars floating in empty space, but dynamic, interconnected systems where matter and energy flowed in complex patterns that shaped their growth and evolution. The brightest of these early galaxies appear to have been remarkably efficient at gathering material from their surroundings. They were cosmic vacuum cleaners, pulling in gas from vast distances and converting it into stars with an efficiency that approaches theoretical limits. This process would have created powerful feedback loops, where stellar winds and supernova explosions would have stirred up the surrounding medium, potentially triggering star formation in neighboring regions. Some theoretical models suggest that these early galaxies might have been connected by streams of dark matter and gas, forming a kind of cosmic circulatory system that channeled material from one galaxy to another. If true, this would mean that galaxy formation in the early universe was a much more collaborative process than we previously imagined. The supermassive black holes at the centers of these galaxies add another layer of complexity to this cosmic ecosystem. As these black holes consumed matter, they would have generated tremendous amounts of energy, creating jets and winds that could influence star formation across enormous distances. The interplay between black hole growth and stellar formation might have been the key mechanism that allowed these early galaxies to grow so massive so quickly. This ecological perspective on early galaxy formation suggests that the universe has always been characterized by interconnectedness and mutual influence. Just as biological ecosystems involve complex webs of relationship between different species, cosmic ecosystems involve intricate relationships between dark matter, ordinary matter, radiation, and the fundamental forces of nature. As you reflect on this cosmic ecology, notice how it might resonate with your understanding of the interconnected systems in your own life. The relationships between family members, the dynamics within communities, the flow of information through social networks. All of these human systems operate according to principles that echo the cosmic processes we're discovering in these ancient galaxies. The discovery of these unusually bright early galaxies raises profound questions about what cosmologists call cosmic fine-tuning, the observation that the fundamental constants of nature seem to be precisely calibrated to allow for the existence of complex structures like galaxies, stars, and ultimately life itself. If the expansion rate of the universe had been slightly faster, matter would have spread out too quickly for gravitational collapse to occur. If it had been slightly slower, the universe would have collapsed back in on itself before stars could form. If the strength of the strong nuclear force had been slightly different, the fusion processes that power stars and create heavy elements wouldn't work properly. These bright early galaxies suggest that the universe might have been even more finely tuned than we realized. Not only were the fundamental constants calibrated to allow for structure formation, but they seem to have been set in such a way that complex structures could form remarkably quickly in the cosmic dawn. Some interpretations suggest, though this remains highly speculative, that this apparent fine-tuning might not be coincidental. Perhaps we exist in a universe specifically suited for rapid complexity development, because only such universes could eventually give rise to observers capable of contemplating their own cosmic origins. This line of thinking leads to what philosophers call the anthropic principle, the idea that the properties of the universe must be compatible with the existence of observers, or we wouldn't be here to observe them. It's a circular argument in some ways, but it points to deep questions about the relationship between consciousness and cosmic evolution. Other interpretations propose that our universe might be one of many in a vast multiverse, each with different fundamental constants. In this view, we happen to find ourselves in a universe compatible with complex structure formation, not because it was designed that way, but because universes incompatible with observers would have no one to notice their existence. These questions touch on some of the deepest issues in philosophy and cosmology. They invite us to consider whether the universe is fundamentally random or whether there might be deeper principles governing its structure and evolution. While science cannot definitively answer these questions, the discoveries we've been exploring provide new data points for philosophical reflection. Take a breath and consider how these cosmic questions about purpose and design might influence your own sense of meaning and direction. The universe that gave birth to these ancient galaxies is the same universe that eventually gave rise to consciousness capable of contemplating its own origins and asking profound questions about existence itself. There's something deeply musical about the way these discoveries are unfolding. Each new observation adds another note to a cosmic symphony that has been playing for 13.8 billion years. The bright early galaxies we've been discussing represent some of the earliest instruments in this cosmic orchestra, their light singing across the darkness in frequencies that we're only now learning to hear. The redshift of these galaxies creates a kind of cosmic Doppler effect, where light that was originally emitted at high frequencies gets stretched to lower frequencies as it travels through expanding space. It's as if the universe itself is conducting a vast cosmic choir, with each galaxy contributing its own voice to a harmony that spans billions of years and countless light years. Astronomers sometimes describe their work in musical terms. They talk about the fundamental frequency of hydrogen, the harmonic series of spectral lines, and the way different elements create distinctive musical signatures in starlight. The process of spectroscopic analysis is like being a cosmic musician, learning to recognize the unique songs that different types of stars and galaxies sing across the electromagnetic spectrum. The dropout technique that led to this discovery relies on recognizing a specific kind of silence in the cosmic symphony. When the Lyman break appears in a galaxy's spectrum, it's like a sudden pause in the music, a moment of quiet that reveals something profound about the source of the sound. These musical metaphors aren't just poetic flourishes, they reflect something deep about the mathematical structure underlying both music and cosmic evolution. The same mathematical relationships that create harmony and rhythm in music also govern the formation of cosmic structures, the orbital mechanics of planetary systems, and the nuclear processes that power stars. Some theoretical physicists have speculated that the universe itself might be understood as a kind of vast musical composition, with the fundamental forces and particles corresponding to different instruments and the evolution of cosmic structure corresponding to the development of musical themes over time. As you listen to this exploration of cosmic mysteries, notice how the rhythm and flow of scientific discovery might mirror the patterns of music that resonate with your own aesthetic sensibilities. There's something inherently beautiful about the process harmonies of uncovering hidden nature, whether in the songs of birds, the structure of mathematical equations, or the light from ancient galaxies. One of cosmic elements of the most profound implications of these early galaxy discoveries involves the democratization of heavy elements throughout the universe. For billions of years, the cosmos consisted almost entirely of hydrogen and helium, the simplest elements created in the Big Bang. Everything else, from the carbon in our bodies to the iron in our blood to the silicon in planetary crusts, had to be forged in the nuclear furnaces of massive stars. These bright early galaxies appear to have accelerated this process of cosmic enrichment dramatically. By converting gas into stars with unprecedented efficiency, they created vast numbers of massive stars that lived fast, burned bright, and died young in spectacular supernova explosions that scattered heavy elements throughout space. This means that the chemical diversity necessary for complex chemistry, rocky planets, and ultimately biological evolution became available much earlier in cosmic history than we previously thought. The universe didn't have to wait billions of years for heavy elements to accumulate slowly. Instead, there may have been a brief period of intense stellar alchemy in the cosmic dawn that seeded space with the ingredients for complexity. The implications extend far beyond academic curiosity about cosmic chemical evolution. If heavy elements became widely available early in the universe's history, it means that potentially habitable planetary systems could have formed billions of years before our own solar system came into existence. Think about what this might mean for the question of life in the universe. If Earth-like planets could have formed when the universe was just a few billion years old, and if life could have emerged on those ancient worlds, then there might have been biological evolution proceeding for 10 billion years or more before life appeared on Earth. This possibility transforms our perspective on our place in the cosmic story. Rather than being among the universe's first experiments with consciousness and intelligence, we might be relative latecomers to a cosmos that has been experimenting with biological complexity for most of its existence. The heavy elements produced by these early galaxies didn't just remain in space randomly. They became incorporated into subsequent generations of stars and planetary systems, creating an ever-expanding web of chemical complexity that continues to enrich the universe today. As you contemplate this cosmic process of elemental democracy, consider how it mirrors the way knowledge, culture, and wisdom spread through human civilizations. Ideas developed in one place and time become available to people in distant places and future generations, creating an ever-expanding web of intellectual inheritance that enriches human experience. As we approach the limits of what these discoveries can tell us, we encounter one of the most humbling aspects of cosmic investigation. No matter how sophisticated our instruments become, no matter how clever our analysis techniques, there will always remain a horizon beyond which we cannot see, a boundary between the knowable and the unknowable in cosmic evolution. The 300 galaxies discovered by Webb are pushing us closer to this fundamental horizon. We're seeing objects that existed when the universe was less than 5% of its current age, but we're still not seeing the very first stars, the very first galaxies, or the transition from cosmic darkness to cosmic dawn. This horizon isn't just a limitation of current technology, it's built into the structure of the universe itself. Before the first stars ignited, there were no sources of visible light in the cosmos. The universe was filled with neutral hydrogen gas that absorbed most electromagnetic radiation, creating what astronomers call the cosmic dark ages. Even with perfect instruments, we could never directly observe this period through conventional astronomy. It's like trying to study a forest by examining only the light that filters through the canopy. We can infer a great deal about what lies beneath, but some aspects of the cosmic story will always remain hidden from direct observation. This encounter with the unknowable is one of the most profound aspects of scientific investigation. It reminds us that knowledge is always partial, always provisional, always open to revision based on new evidence and new perspectives. Yet there's something beautiful about this limitation. It means that the universe will always retain an element of mystery, always offer new puzzles to solve and new horizons to explore. The questions raised by these 300 galaxies will likely lead to new questions that we haven't even thought to ask yet. Some of these questions might require entirely new forms of investigation. Future astronomers might study the cosmic dark ages through gravitational waves, neutrino emissions, or forms of radiation we haven't yet learned to detect. They might develop theoretical models so sophisticated that they can reconstruct the invisible phases of cosmic evolution with remarkable precision. But even then, even with technologies we can barely imagine, there will always remain aspects of cosmic history that exist beyond the horizon of direct investigation. And perhaps that's as it should be. Perhaps the universe needs to retain some secrets, some aspects of its story that can only be approached through wonder, imagination, and the kind of profound humility that comes from recognizing the limits of our understanding. Take a moment to consider how this cosmic horizon of the unknowable might inform your approach to mystery and uncertainty in your own life. Just as the universe retains aspects that science cannot fully penetrate, your own inner experience contains depths and complexities that may never be completely understood or explained. As our journey through these cosmic mysteries draws toward its conclusion, we find ourselves in a curious position. We began with 300 mysterious galaxies that challenged our understanding of the universe, and we end with an even deeper appreciation for the profound mysteries that remain to be explored. This is the eternal return of wonder that characterizes the scientific enterprise. Each answer leads to new questions. Each discovery opens new horizons of investigation. Each technique for probing cosmic history reveals new aspects of the universe that we didn't know. The bright early galaxies discovered by Webb are teaching us that cosmic evolution is far more creative, dynamic, and surprising than we ever imagined. But they're also teaching us something equally important about the process of discovery itself. They're showing us that the universe has an inexhaustible capacity to surprise us, to challenge our assumptions, and to invite us into deeper levels of understanding and appreciation. This capacity for surprise isn't a bug in the system of scientific investigation. It's a feature. It's what keeps science alive, vibrant, and perpetually fascinating. Without the capacity for surprise, scientific investigation would become mere catalogue making, a process of confirming what we already know rather than discovering what we never imagined. The researchers who made this discovery spent months analysing their data, checking their results, and trying to understand what they were seeing. But the most profound moment might have been that first instant when they realised they were looking at something that didn't fit any existing model, something that required them to expand their vision of what was possible in the early universe. That moment of recognition, when familiar patterns suddenly reveal unfamiliar depths, is at the heart of all genuine discovery. It's the moment when the known world suddenly becomes larger, more complex, and more beautiful than it was before. As you reflect on this process of cosmic discovery, notice how it might mirror moments of insight and revelation in your own experience. Sometimes, our most profound personal growth comes not from confirming what we already believe about ourselves, but from encountering aspects of our own nature that surprise and challenge us. The 300 galaxies that started this exploration have become teachers, not just about cosmic evolution, but about the nature of knowledge, mystery, and the endless capacity for growth and transformation that characterizes both the universe and human consciousness. Science is not a destination, but a journey, and the discoveries we've explored today represent just one chapter in an ongoing story that connects us to the deepest mysteries of existence. The light from these ancient galaxies has been travelling toward us for over 13 billion years, and it arrived at exactly the right moment in human history for us to capture it, analyse it, and learn from it. But the story doesn't end with our current understanding. Future observations will reveal new details about these galaxies and their role in cosmic evolution. New theoretical models will emerge to explain their rapid formation and extraordinary brightness. New questions will arise that we haven't even thought to ask yet. The next generation of space telescopes will push even deeper into the cosmic past, perhaps finally revealing the very first stars and the transition from cosmic darkness to cosmic dawn. Ground-based observatories will conduct detailed studies of these early galaxies, measuring their chemical compositions, stellar populations, and internal dynamics with unprecedented precision. Each of these future discoveries will add new chapters to the cosmic story we've been exploring. They will confirm some of our current ideas, challenge others, and undoubtedly reveal aspects of cosmic evolution that we haven't yet imagined. But perhaps the most important aspect of this continuing story is the way it connects us to the ongoing process of cosmic evolution itself. We're not separate observers studying an external universe. We're participants in the same cosmic story that began with these early galaxies. The elements in our bodies were forged in stellar cores similar to those that powered these ancient galaxies. The physical laws that govern our thoughts and emotions are the same laws that governed galactic formation in the cosmic dawn. The capacity for complexity, creativity, and consciousness that we experience in our daily lives reflects the same fundamental principles that allowed the universe to evolve from simplicity to sophistication over billions of years. This connection goes beyond mere poetry or metaphor. It's a literal, physical connection mediated by the same atoms, the same forces, and the same mathematical relationships that have been operating since the universe began. As you prepare to continue your own journey through life, carry with you the perspective that these cosmic discoveries offer. You're not just a temporary arrangement of matter and energy. You are a way that the universe has learned to know itself, to ask questions about its own nature, and to experience wonder at its own profound creativity and beauty. The same cosmos that gave birth to those 300 mysterious galaxies continues to evolve through your thoughts, your relationships, and your capacity to find meaning in the ongoing process of discovery and growth. Remember that the light from distant galaxies connects you to cosmic history, but the light of consciousness connects you to cosmic destiny. In ways we're only beginning to understand, the universe's capacity for awareness, creativity, and transformation finds expression through beings like you who can contemplate their own cosmic origins and imagine possibilities that don't yet exist. The story continues, and you're both its narrator and its protagonist, both its observer and its participant. The mysteries we've explored today will lead to new mysteries tomorrow, and the sense of wonder that drives scientific discovery is the same sense of wonder that can illuminate every moment of your daily experience. As we conclude this exploration of cosmic mysteries, remember that the same universe that created those ancient galaxies continues to unfold new possibilities through quantum processes that operate at the smallest scales of reality. In our next journey together, we'll discover how the quantum nature of reality itself might be shaping the very decisions you make every moment of your life, connecting cosmic evolution to the intimate reality of choice and possibility in the quantum decision that's already shaping your future. Until then, may your own sense of wonder remain as bright as those ancient cosmic beacons, illuminating new possibilities in every direction you choose to look. As we drift deeper into these cosmic revelations, there's something almost quantum mechanical about how these ancient galaxies seem to exist in multiple states simultaneously until the moment of observation. Before Webb's golden mirrors captured their light, these objects existed in a kind of cosmic superposition, both incredibly bright and impossibly dim according to our theoretical expectations. The act of measurement, of finally gathering enough photons to confirm their existence and properties, collapsed this uncertainty into definite knowledge. It's a process that mirrors, though this remains a speculative connection rather than proven science, the way quantum systems behave at the smallest scales of reality. Consider how the researchers approach their analysis of these 300 candidates. Each object existed in a state of potential confirmation, simultaneously ancient galaxy, nearby imposter, and instrumental artifact, until careful spectroscopic analysis could determine its true nature. The process of cosmic discovery shares this quality of uncertainty resolution with quantum measurement, though we must be careful not to overstate this parallel. What's particularly fascinating is how the properties of these galaxies seem to emerge from their interactions with the cosmic environment around them. Just as quantum particles can become entangled with their surroundings in ways that influence their behavior, these early galaxies appear to have been shaped by complex feedback loops involving dark matter, gas dynamics, and the radiation from neighboring stellar nurseries. The supermassive black holes at their centers add another layer of quantum-like mystery. These objects exist at the boundary between the classical physics that governs large-scale cosmic structures and the more exotic physics that operates near event horizons, where space and time themselves become distorted. As you contemplate these cosmic mysteries, notice how they invite us to think about the fundamental relationship between observation and reality. The light from these galaxies carries information that has been preserved across billions of years. But that information only becomes meaningful when it encounters conscious observers capable of decoding its message. There's something deeply satisfying about discovering that complexity and organisation can emerge spontaneously from apparent chaos. And these bright early galaxies represent one of the most dramatic examples of this principle operating on cosmic scales. They formed during an era when the universe should have been too young and disorganized to support such sophisticated structures. This emergence of order from disorder reflects what complexity theorists call self-organization, the tendency of certain systems to spontaneously develop structure and coherent behavior without external direction. While the mechanisms are different, the same principle operates in everything, from the formation of crystals to the development of biological ecosystems to the organization of neural networks in the brain. The early universe provided ideal conditions for this kind of emergent complexity. The higher density of matter meant that gravitational interactions were stronger, allowing structures to form more quickly than they do today. The absence of heavy elements paradoxically might have made star formation more efficient by reducing the mechanisms that normally regulate and slow the process. These galaxies also demonstrate what systems theorists call phase transitions, sudden shifts from one type of organization to another. The transition from a universe dominated by smooth distributions of dark matter and gas to one containing bright, massive galaxies represents a cosmic phase transition comparable to water suddenly freezing into ice, or a magnetic material becoming magnetized below a critical temperature. But perhaps most intriguingly, these early galaxies exhibit what appears to be coordinated behavior across vast distances. Their formation seems to have been synchronized in ways that suggest large-scale patterns of organization that we're only beginning to understand. Some interpretations suggest, though this remains highly speculative, that the early universe might have operated according to principles of collective behavior that allowed widely separated regions to influence each other's development. This could involve exotic physics, unknown properties of dark matter, or simply the subtle effects of long-range gravitational correlations. Take a breath and consider how these patterns of cosmic emergence might resonate with your own experience of growth and development. Sometimes the most significant changes in our lives happen not through gradual accumulation, but through sudden reorganizations that bring new levels of complexity and capability into being. Every photon captured by Webb's instruments carries within its wavelength and intensity a compressed archive of information about the conditions that existed when it was first emitted over 13 billion years ago. This information has been preserved with extraordinary fidelity during its journey across cosmic space, protected by the fundamental conservation laws that govern electromagnetic radiation. The process of extracting this information requires sophisticated techniques that border on the miraculous. Astronomers must account for how the expansion of space has stretched the light, how intergalactic gas has absorbed certain wavelengths, and how gravitational fields have bent the photon's path during its billion-year journey. What emerges from this analysis is a detailed portrait of physical conditions that no longer exist anywhere in the observable universe. We can measure the temperature of gas clouds that dissipated billions of years ago, the chemical composition of stars that exploded before our solar system formed, and the rate of stellar birth in galactic nurseries that have long since evolved into something completely different. This preservation of ancient information in light represents one of the universe's most elegant solutions to the problem of cosmic memory. Unlike human memory, which can be altered by emotion and expectation, the information encoded in starlight remains objective and unchanging throughout its journey across space and time. The researchers analysing this data become cosmic archaeologists, reconstructing entire civilizations of stars and gas from fragments of ancient light. Each spectrum tells a story about nuclear fusion rates, stellar winds, supernova explosions, and the gradual enrichment of space with heavy elements. But there's something almost mystical about the realization that this information has been traveling toward us for longer than complex life has existed on Earth. The light we're analyzing began its journey when the universe was young and wild, and it arrives at our detectors just as human consciousness has developed the sophistication necessary to decode its meaning. As you reflect on this cosmic information transfer, consider how it mirrors the way knowledge and wisdom are preserved and transmitted across generations in human culture. Stories, insights, and understanding can travel across centuries of human experience, arriving at exactly the right moment to illuminate new possibilities for growth and discovery. One of the most profound aspects of these discoveries involves the way they reveal connections between processes operating on vastly different scales of space and time. The formation of individual stars within these ancient galaxies influenced the chemical evolution of entire galactic systems, which in turn affected the large-scale structure of the cosmic web itself. This multiscale organization reflects what scientists call hierarchical complexity, where patterns at one level of organization influence and are influenced by patterns at both smaller and larger scales. The quantum processes governing nuclear fusion in stellar cores ultimately determine the properties of galaxies containing billions of stars, which in turn shape the evolution of cosmic structure across hundreds of millions of light years. The feedback loops operating within these early galactic systems demonstrate remarkable sophistication. Massive stars would form, live brief intense lives, and explode as supernova, enriching the surrounding gas with heavy elements and triggering the formation of new generations of stars with different properties. This process created a kind of cosmic metabolism, where galaxies grew and evolved through cycles of stellar birth, death, and renewal. The supermassive black holes at the centers of these galaxies added another layer of complexity to this multiscale organization. As they consumed matter, they generated powerful jets and winds that could influence star formation across the entire galaxy and beyond. The growth of these black holes was intimately connected to the growth of their host galaxies in ways that created stable, self-regulating systems. Some theoretical models suggest that these early galactic systems might have exhibited what complexity theorists call emergent intelligence, the capacity for coordinated behavior that arises spontaneously from the interactions of simpler components. While we must be careful not to anthropomorphize cosmic processes, there's something undeniably sophisticated about the way these systems organize themselves and adapted to changing conditions. This multi-scale perspective invites us to consider how similar principles might operate in other complex systems, including biological ecosystems, neural networks, and social organizations. The same mathematical relationships that govern the interaction between stellar formation and galactic evolution also appear in the dynamics of forest ecosystems, the organization of brain activity, and the flow of information through human communities. Take a moment to notice how this cosmic perspective might influence your understanding of the interconnected systems in your own life. The decisions you make as an individual contribute to family dynamics, which influence community patterns, which shape larger social and cultural trends that eventually affect global developments. As these discoveries continue to unfold, they're teaching us something profound about the relationship between knowledge and mystery in scientific investigation. Each new piece of information about these ancient galaxies simultaneously answers old questions and raises new ones, creating an ever-expanding frontier between the known and the unknown. The spectroscopic confirmation of objects like JD's GS-Z14-0 provides definitive evidence that massive luminous galaxies existed in the cosmic dawn. But this confirmation also deepens the mystery of how such objects could have formed so quickly and grown so large in the time available. This dance between certainty and mystery is characteristic of all genuine scientific discovery. Unlike pseudo-scientific claims that pretend to explain everything, real science embraces uncertainty. Measurement comes with error as an essential feature of the investigative process. Each observation, each theory remains provisional, and each model acknowledges the limitations of current understanding. The researchers working on this discovery exemplify this scientific humility. They present their findings with careful attention to statistical significance, systematic uncertainties, and alternative explanations. They acknowledge what they know, what they don't know, and what they might never be able to know given the fundamental limitations of observational astronomy. Yet there's something deeply satisfying about this embrace of uncertainty. It means that the universe will always retain elements of mystery, always offer new puzzles to solve and new horizons to explore. The questions raised by these 300 galaxies will likely inspire decades of future research, leading to discoveries we can barely imagine today. This scientific approach to mystery stands in interesting contrast to other ways of engaging with the unknown. Rather than claiming definitive answers or retreating into comfortable certainties, science maintains a delicate balance between confidence in method and humility about conclusions. Some interpretations suggest, though this remains philosophically speculative, that this scientific embrace of uncertainty reflects something deep about the nature of reality itself. Perhaps the universe is fundamentally open-ended, characterized more by creative possibility than by predetermined outcomes. As you contemplate this balance between knowledge and mystery, consider how it might inform your approach to uncertainty in your own life. Rather than seeing the unknown as something to be feared or quickly resolved, you might learn to appreciate it as a space of potential and creative possibility. These bright early galaxies are revealing that cosmic evolution operates more like an ecological system than a simple mechanical process. The formation and growth of galaxies involves complex webs of relationship and mutual influence that span enormous distances and timescales. The chemical elements produced by stellar nucleosynthesis in one galaxy can be ejected by supernova explosions and galactic winds, traveling through intergalactic space to enrich neighboring systems. This creates a kind of cosmic nutrient cycle, where the waste products of stellar evolution in one location become the raw materials for planet formation and biological evolution in another. The large-scale structure of the universe, with its filaments of dark matter and ordinary matter, provides the scaffolding within which this ecological process unfolds. Galaxies form at the intersections of these cosmic filaments, where matter flows together like water collecting at the bottom of a watershed. But the analogy goes deeper than mere material exchange. These early galactic systems appear to have developed what ecologists call keystone relationships, where certain components have disproportionate influence on the overall system dynamics. The supermassive black holes at galactic centers might have served this keystone function, regulating star formation and chemical evolution across entire galactic ecosystems. The discovery that massive galaxies form so early in cosmic history suggests that this ecological organization developed much more quickly than previously thought. Rather than requiring billions of years of gradual development, cosmic ecosystems might have achieved remarkable sophistication within the first few 100 million years after the Big Bang. This rapid development of cosmic ecology has profound implications for understanding the potential for life and intelligence in the universe. If complex chemical environments became available early in cosmic history, it means that the conditions necessary for biological evolution might have existed for most of the universe's lifetime. The interconnectedness revealed by these discoveries also suggests that consciousness and intelligence, when they do emerge, become part of the cosmic ecosystem in ways that influence its further evolution. Through scientific observation and technological activity, conscious beings like ourselves become active participants in the ongoing development of cosmic complexity. As you reflect on this ecological perspective on cosmic evolution, notice how it might deepen your sense of connection to the larger systems of which you're a part. Just as these ancient galaxies influenced each other across vast distances, your own thoughts and actions ripple outward through social and environmental networks in ways that contribute to the ongoing evolution of complexity on Earth. There's something almost architectural about the way these discoveries are being constructed through the careful accumulation of observational evidence, theoretical modelling, and collaborative interpretation. Each piece of data is like a building block in an ever-growing structure of understanding that connects us to cosmic history. The process began with Webb's deep field observations, systematic surveys that captured light from thousands of cosmic sources across carefully selected patches of sky. These observations provided the raw material, the cosmic equivalent of archaeological artifacts that preserve information about ancient conditions and processes. The next phase involved sophisticated image analysis, where researchers applied the dropout technique to identify candidate distant galaxies based on their colour signatures. This process is like sorting through archaeological finds to identify objects that might belong to specific historical periods. Spectroscopic follow-up observations represent the most detailed level of analysis, where individual objects are studied with high precision to determine their distances, compositions, and physical properties. This is analogous to the careful laboratory analysis that archaeologists perform on their most significant finds. But perhaps the most important phase involves the interpretation and integration of these findings with existing theoretical frameworks. This is where individual discoveries become part of larger narratives about cosmic evolution, where specific observations illuminate general principles about how the universe works. The collaborative nature of this process reflects something beautiful about how knowledge grows in the scientific community. Researchers from different institutions, working with different instruments and analytical techniques, contribute pieces to a puzzle that none of them could solve individually. This temporal architecture of discovery operates on multiple timescales simultaneously. The light being analysed has been travelling for over 13 billion years. The instruments used to capture it took decades to design and build. The analysis and interpretation process unfolds over months and years, and the implications for our understanding of cosmic evolution will influence scientific thinking for decades to come. Some interpretations suggest, though this remains metaphorically rather than literally true, that this process of scientific discovery mirrors the way consciousness itself constructs understanding from fragments of sensory experience. We don't perceive reality directly, but rather construct models of reality based on incomplete information, constantly updating and refining those models as new evidence becomes available. Take a breath and consider how this temporal architecture of understanding might apply to your own process of making sense of life experience. Like cosmic archaeologists, you're constantly gathering fragments of information from your interactions with the world, assembling them into narratives that help you navigate present circumstances and anticipate future possibilities. As we near the completion of our journey through these cosmic mysteries, there's something profoundly moving about the realization that we're connected to these ancient galaxies through the most intimate possible relationship. The light that left them 13 billion years ago is over now, entering your consciousness, creating a direct link between your present moment of awareness and events that occurred when the universe was young. This connection transcends mere intellectual understanding. At the level of physical reality, photons that were emitted by hot gas and newborn stars in the cosmic dawn are now stimulating neural activity in your brain, contributing to the thoughts and feelings you're experiencing right now. You're not just learning about these ancient galaxies, you're literally incorporating their light into your consciousness. The wavelength of this ancient light carries information that has been preserved with extraordinary fidelity throughout its journey across expanding space. The spectral lines that reveal the chemical composition of primordial gas clouds are the same lines that astronomers measure in their laboratories today. The physical laws that governed stellar nucleosynthesis in the cosmic dawn are the same laws that govern nuclear processes in the present moment. This preservation of information across cosmic time suggests something profound about the nature of reality itself. The universe appears to be constructed in such a way that meaningful patterns can persist across vast scales of space and time, allowing the past to remain accessible to present investigation and contemplation. The researchers who made this discovery have become intermediaries in this ancient conversation between cosmic past and conscious present. Through their patient work of observation, analysis, and interpretation, they've translated the language of starlight into concepts that human consciousness can comprehend and appreciate. But the conversation doesn't end with scientific understanding. These discoveries invite each of us to participate in the ongoing dialogue between consciousness and cosmos, between the human capacity for wonder and the universe's capacity for surprise. Some interpretations suggest, though this remains poetically rather than scientifically precise, that consciousness itself might be understood as the universe's way of coming to know itself. Through conscious beings like ourselves, the cosmos develops the capacity for self-reflection, for asking questions about its own nature and origins. As you prepare to carry these cosmic insights into your daily experience, remember that the same universe that gave birth to those ancient galaxies continues to unfold new possibilities through every moment of conscious awareness. The capacity for wonder, curiosity, and growth that drives scientific discovery is the same capacity that can illuminate every aspect of your personal journey through life. These discoveries about ancient galaxies ultimately return us to some of the most fundamental questions that conscious beings can ask. Who are we? Where did we come from? What is our place in the larger cosmic story? And perhaps most intriguingly, what possibilities does the future hold for consciousness and complexity in an ever-evolving universe? The bright early galaxies we've explored suggest that the universe has been experimenting with complexity and organization for most of its existence. Rather than being a recent development, the capacity for rapid growth, sophisticated structure, and dynamic evolution appears to be a fundamental feature of cosmic reality. This cosmic creativity manifests at every scale of organization, from the quantum processes that govern atomic interactions to the large-scale flows of matter and energy that shape galactic evolution. The same principles that allowed ancient galaxies to grow massive and luminous in the cosmic dawn continue to operate through biological evolution, neural development, and cultural transformation on Earth. The discovery that supermassive black holes existed so early in cosmic history raises particularly profound questions about the relationship between destruction and creation, between the forces that tear structures apart and those that build them up. These cosmic engines of transformation appear to play essential roles in regulating galactic evolution and enabling the emergence of ever greater complexity. Perhaps most remarkably, these ancient processes eventually gave rise to conscious observers capable of contemplating their own cosmic origins. The nuclear fusion that powered those early stars created the heavy elements that make up our bodies. The chemical enrichment they provided made possible the rocky planets where life could emerge. The gravitational dynamics they initiated shaped the cosmic web within which our local group of galaxies now resides. This chain of cosmic causation connects us directly to events that occurred over 13 billion years ago, making us not separate observers of cosmic history, but participants in its ongoing unfoldment. Every thought you think, every emotion you feel, every decision you make represents a continuation of the creative processes that began with those ancient galactic beacons. The questions these discoveries raise don't have simple answers, and perhaps that's as it should be. Like the universe itself, consciousness appears to be characterized more by creative exploration than by final destinations, more by the capacity to ask new questions than by the ability to provide definitive answers. Take a moment to appreciate how these cosmic mysteries might inform your approach to the fundamental questions in your own life. Rather than seeking final answers about purpose, meaning, and direction, you might learn to embrace the ongoing process of discovery, growth, and transformation that connects your personal journey to the larger cosmic story of which you're an essential part. In the end, these 300 mysterious galaxies are teaching us that the universe is far more creative, dynamic, and surprising than we ever dared imagine. They remind us that we live in a cosmos characterized by endless possibility, where consciousness and complexity continue to emerge in ways that transcend our current understanding. As we prepare to transition from cosmic mysteries to quantum realities, remember that the same universe that created those ancient galactic beacons operates according to quantum principles that some interpretations suggest, though this remains scientifically unproven, might influence the very nature of choice, possibility, and consciousness in your daily experience. The cosmic journey we've shared connects directly to our next exploration, where we'll discover how the quantum nature of reality itself might be shaping the decisions that define your future. Join me as we venture into the quantum decision that's already shaping your future, where the mysteries of cosmic evolution meet the intimate reality of human consciousness, and the profound questions of how consciousness navigates the quantum landscape of possibility that underlies every moment of experience. Until that next journey begins, carry with you the wonder these ancient galaxies inspire, and remember that you are both a product of cosmic evolution and an agent of its continued unfoldment, a conscious participant in the universe's ongoing exploration of its own infinite creative potential. As we transition from the vast scales of cosmic evolution to the intimate realm of quantum reality, there's something almost poetic about how these ancient galaxies connect to the smallest scales of existence. The same fundamental forces that shaped galactic formation 13 billion years ago continue to operate through the quantum processes that some interpretations suggest, though this remains scientifically unproven, might influence the texture of consciousness itself. Consider for a moment how the light from these distant galaxies arrives at your retina one photon at a time, each particle of light carrying its quantum properties intact across billions of years of cosmic travel. These individual photons, behaving according to the strange rules of quantum mechanics, somehow combine to create the coherent visual experience you might have when looking at Webb's images of ancient cosmic light. This transition from quantum to classical, from individual particles to collective experience, mirrors something profound about how consciousness itself might emerge from the quantum substrate of neural activity. While we must be careful not to overstate these connections, there's something deeply satisfying about recognizing that the same mathematical formalism that describes galactic evolution also governs the behavior of the subatomic particles that make up your brain. The researchers analyzing these cosmic discoveries work with instruments that rely fundamentally on quantum mechanical principles. The detectors in Webb's cameras operate by converting individual photons into electrical signals through quantum photoelectric effects. The computers they use to process the data rely on quantum tunneling effects in semiconductor devices. Even their theoretical models incorporate quantum field theory to understand the fundamental forces that shaped early cosmic evolution. This quantum foundation of modern astronomy suggests something beautiful about the interconnectedness of reality across all scales of organization. The same principles that govern the behavior of electrons in laboratory experiments also determine how matter clumped together to form the first galaxies in the cosmic dawn. Take a breath and consider how this quantum perspective might influence your understanding of the relationship between the very small and the very large in your own experience. The thoughts arising in your consciousness emerge from quantum processes in neural networks, yet somehow give rise to contemplation of galaxies spanning millions of light years. One of the most intriguing aspects of quantum mechanics involves the role of observation in determining the properties of quantum systems. While the details remain contentious among physicists, there's something profound about the idea that the act of measurement can influence the very thing being measured, collapsing quantum possibilities into definite outcomes. This observer effect, though it operates primarily at microscopic scales, invites us to consider how the process of cosmic discovery itself might participate in the ongoing evolution of our understanding of reality. When astronomers observe these ancient galaxies, they're not just passively recording pre-existing information, they're actively participating in a process that transforms raw data into meaningful knowledge about cosmic evolution. The 300 galaxies we've been exploring existed in a kind of observational superposition before Webb's instruments captured their light. They were simultaneously ancient cosmic beacons and potential instrumental artifacts until careful analysis could determine their true nature. The process of scientific investigation collapsed this uncertainty into definite knowledge, much as quantum measurement collapses wave functions into specific outcomes. Of course, we must be careful not to overextend this analogy. The galaxies themselves existed regardless of our observation, and their properties were determined by physical processes operating billions of years ago. But there's something meaningful about recognizing that scientific discovery involves an active relationship between conscious observers and the phenomena they study. Some interpretations suggest, though this remains philosophically speculative rather than scientifically proven, that consciousness itself might be understood as a quantum phenomenon, emerging from the complex interactions of quantum processes in neural networks. If true, this would mean that the same universe that gave birth to those ancient galaxies eventually evolved the capacity for conscious observation through quantum mechanical processes in biological systems. The measurement problem in quantum mechanics, which concerns how definite outcomes emerge from quantum possibilities, finds an interesting parallel in the process of scientific discovery. Just as quantum measurement requires interaction between a quantum system and a measuring apparatus, scientific understanding requires interaction between conscious observers and the phenomena they investigate. This interactive aspect of knowledge creation suggests that we're not separate from the cosmic story we're trying to understand. We're participants in the ongoing evolution of cosmic complexity, conscious beings through whom the universe develops the capacity to comprehend its own history and contemplate its future possibilities. As you reflect on this participatory aspect of cosmic discovery, notice how it might resonate with your own experience of learning and understanding. Knowledge doesn't just accumulate passively in consciousness, it emerges through active engagement with experience, through the quantum processes of neural activity that somehow give rise to insight, wonder, and comprehension. Quantum entanglement, one of the most mysterious phenomena in physics, demonstrates how particles can maintain instantaneous correlations across vast distances, as if they remain connected in ways that transcend classical space and time. While this effect operates primarily at microscopic scales, it invites us to consider how the past and present might remain entangled in ways that influence our understanding of cosmic evolution. The light from these ancient galaxies carries quantum correlations that have been preserved throughout its billion-year journey across expanding space. The photons arriving at Webb's detectors retain information about the quantum states of atoms in stellar atmospheres that existed when the universe was young. In some sense, these particles serve as quantum messengers, maintaining a direct physical connection between cosmic past and conscious present. This preservation of quantum information across cosmic time suggests something profound about the nature of reality itself. The universe appears to be constructed in such a way that meaningful correlations can persist across enormous scales of space and time, connecting distant events through networks of quantum relationship that we're only beginning to understand. Some interpretations suggest, though this remains highly speculative and unproven, that consciousness itself might exhibit something analogous to quantum entanglement, with past experiences, present awareness, and future possibilities, maintaining correlations that transcend ordinary notions of temporal sequence. While we must be extremely cautious about such claims, there's something intriguing about the possibility that memory, imagination, and immediate experience might be more interconnected than classical psychology suggests. The process of scientific discovery demonstrates its own form of temporal entanglement. The questions that drive current research are shaped by discoveries made decades or centuries ago, while the answers we find today will influence the questions that future generations will ask. Knowledge itself exhibits a kind of non-local correlation across time, where insights from one era can suddenly illuminate problems that seemed intractable in another. The ancient galaxies we've been exploring existed billions of years before Earth formed, yet their influence on cosmic chemical evolution helped create the conditions that eventually allowed life and consciousness to emerge. In this sense, our present moment of awareness is quantum entangled with events that occurred in the cosmic dawn, connected through chains of causation that span the entire history of the universe. This temporal entanglement extends to your personal experience as well. The thoughts arising in your consciousness right now are influenced by neural patterns established through past experience, yet they also influence the neural configurations that will shape future thoughts and feelings. Mind and memory exhibit their own form of quantum-like correlation across time. Take a moment to appreciate how this entanglement perspective might deepen your sense of connection to both cosmic history and personal experience. You're not an isolated observer contemplating distant events, but rather an active participant in networks of relationship that connect present moment awareness to the deeper structures of space, time, and consciousness. Heisenberg's uncertainty principle, one of the foundational insights of quantum mechanics, demonstrates that certain pairs of properties cannot be measured simultaneously with perfect precision. The more accurately you determine a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our measuring instruments, it's a fundamental feature of quantum reality itself. This principle of irreducible uncertainty finds fascinating parallels in our attempts to understand cosmic evolution. The more precisely we try to pin down the exact properties of these ancient galaxies, the more questions arise about the processes that created them. Each answer leads to new uncertainties. Each measurement opens new horizons of investigation. Consider how the discovery of these 300 bright early galaxies has simultaneously increased our knowledge and deepened our appreciation for what we don't know. We now have definitive evidence that massive, luminous galaxies existed in the cosmic dawn, but this confirmation has raised profound new questions about the mechanisms of early structure formation. The uncertainty principle suggests that this dynamic relationship between knowledge and mystery isn't a temporary limitation that better instruments might overcome. It might be a fundamental feature of reality itself, a cosmic reminder that perfect knowledge of any complex system is impossible because the act of investigation inevitably disturbs what we are trying to understand. Some interpretations suggest, though this remains philosophically speculative, that consciousness itself operates according to principles analogous to quantum uncertainty. The more precisely we try to analyze our immediate experience, the more we disturb the natural flow of awareness. Meditation traditions have long recognized this paradox, teaching that direct understanding often emerges through relaxed attention rather than focused analysis. This uncertainty perspective invites us to embrace what scientists call negative capability, the capacity to remain comfortable with doubt, uncertainty, and mystery rather than irritably reaching after fact and reason. The most profound discoveries often emerge not from eliminating uncertainty, but from learning to work creatively with it. The ancient galaxies we've explored embody this principle beautifully. They exist at the limits of observational possibility, where every measurement comes with error bars and every interpretation remains provisional. Yet it's precisely this encounter with the limits of knowledge that makes these discoveries so profound and transformative. In your own process of understanding and growth, you might experiment with applying this uncertainty principle. Rather than seeking final answers about purpose, meaning, and direction, you might learn to appreciate the creative tension between knowing and not knowing, between confidence and curiosity. As you contemplate these quantum parallels to cosmic discovery, notice how embracing uncertainty might paradoxically increase your capacity for insight and understanding. Sometimes, the most profound revelations emerge not when we pin down exact answers, but when we learn to dance gracefully with the fundamental mysteries that make existence endlessly fascinating. The many worlds interpretation of quantum mechanics suggests that every quantum measurement creates a branching of reality into parallel universes, each containing a different outcome of the measurement process. While this remains one of several competing interpretations of quantum theory, it offers a fascinating perspective on the relationship between possibility and actuality in cosmic evolution. Consider how the formation of these early galaxies involved countless quantum processes, from the nuclear fusion reactions in stellar cores to the gravitational interactions between dark matter particles. If the many worlds interpretation is correct, then every quantum event in these ancient systems created branches of reality where cosmic evolution proceeded differently. In some of these parallel universes, perhaps the early galaxies formed even more rapidly than in our timeline. In others, they might have remained small and dim, never achieving the brightness that Webb has detected. Still other branches might have seen entirely different patterns of cosmic evolution, with alternative forms of structure and organization that we can barely imagine. In this many worlds perspective, while remaining scientifically unproven, invites us to consider how the cosmic story we've been exploring represents just one path through an infinite garden of forking possibilities. The universe we observe and inhabit emerge from countless quantum choices that shape the trajectory of cosmic evolution from the Big Bang to the present moment. These 300 mysterious galaxies have carried us on a journey from the cosmic dawn to the quantum foundations of reality itself, revealing a universe far more creative, dynamic, and interconnected than we ever dared imagine. They've shown us that the cosmos has been experimenting with complexity and consciousness for most of its existence, and that we are not separate observers of this cosmic story, but active participants in its ongoing unfoldment. Through the patient work of astronomers peering back through 13 billion years of light time, we've glimpsed a universe that defies our expectations at every turn. These ancient beacons remind us that mystery and wonder are not obstacles to understanding, but essential features of a reality that remains endlessly capable of surprise. As you carry these cosmic insights into your daily experience, remember that the same forces that shaped those primordial galaxies continue to operate through every moment of your conscious awareness, connecting you to the deepest mysteries of existence itself. The light from distant stars connects you to cosmic history, but the light of consciousness connects you to cosmic possibility, where quantum mechanics meets human experience in the quantum decision that's already shaping your future.